Okay, we're going to start section 2.1 by reading this motivating example. And I'm not actually going to work this example right now. We'll work it at the end of class on Wednesday, but I want you to kind of see, and I have these at the beginning of most sections of the notes, sort of why we're studying this or maybe what the end goal is. So if you'll see these three problems, they're talking about a car traveling a certain distance. So in the first one, it travels 30 miles per hour, with an average velocity of 40 miles per hour, and then 30 minutes at 60 miles per hour. And it wants to know what's the average velocity of the car for the 60-mile trip. And the next question talks about another car travels 30 minutes at 40 miles per hour and then 30 minutes at 60 miles per hour. And it wants to find the average velocity of this car in the 1 hour period. And then the last one is a car is to travel 2 miles and it goes the first mile at an average velocity of 30 miles per hour. And the driver wants to average 60 miles per hour for the entire 2-mile trip. And is this possible? Explain. So by the end of this section, we should be able to answer these questions based on sort of what we're going to look at about limits, rates of change, and tangent lines. So first, we're going to talk about what is a tangent line. And we've actually probably seen this before, or you hopefully have seen it at some point in your life. And where you may have seen it before is in like a geometry or a trig class. Usually you have a circle. And we talk about a tangent line, something that's tangent to a circle, is a line that touches your curve at one point. And like you've probably seen that with, like I said, circles being the curve. But what we're going to do in this class when we talk about tangents is talk about them more generally. So if you have sort of any sort of function, looks like this maybe, then we can talk about the tangent line at any one point. So we could pick this point and draw the line that touches at that one point. Or pick this point right here and draw the line that touches at that one point. Or we could pick a point here and draw the line that touches at that one point, sort of at that space. So that's what we're talking about when we talk about tangent lines. That doesn't mean that it may not intersect the graph at a later stage, like way over here or something, but it's really the line that if you draw it, and it's really hard to draw with this marker, it's the line that touches right there at that curve at that point. And I don't think any of these necessarily do that exactly, but hopefully you get the idea. So what this sort of class is going to do is really look at thinking about tangent lines and secant lines and their relationship. And that's what calculus, the whole first half of what we're going to talk about, is really going to be about, is these two things, tangents and secants, and how they're related. So what we're going to end up doing is using the slope of secant lines, and we'll talk about what a secant line is in just a second, to approximate the slope of a tangent line. And if you're asking about sort of what a secant line is, so if we go back up here in our pictures and I want to draw a secant line on this curve, a secant line you're usually given 2 points, so maybe this point and this point, and then you would draw the secant line between, it's the point connecting those 2 points. So it may go through the line or whatever, so it's just take any 2 points. So if you were to come over here on our picture, if I were to take this point and this point, I could draw a secant line through those 2 points. So it's the line that goes through 2 points. So secant line goes through 2 points. Okay, and so the idea is that we're going to use secant lines to approximate these tangent lines. And I'm going to show you all a little animation in class on Wednesday to help you see that a little bit better. I just wanted to do one more thing before class, and that's pretty much write down the formula for these average velocity and instantaneous velocity. And that way we can then do plenty of examples in class and also look at sort of visually what these secant lines and tangent lines are doing. So the application way to talk about secant lines and tangent lines is to talk about what's known as average velocity or average rate of change. That's what this ROC stands for. So this means rate of change. And then instantaneous velocity or rate of change. So average velocity is your change in position, so wherever you might be, divided by the change in time. And that's usually written delta y over delta x. If you're like physics or something, sometimes they do that. That's a change in y over change in x. And then instantaneous velocity is really the limiting value And I know we haven't used that word limit, but hopefully with the animation that'll help make what that means, of the average velocities. And so in other words, the secant line, or the average velocity, so secant and average velocity are pretty much the same thing. The average velocity is the application way to think about it. And then tangent lines, right, those are the ones that are going to be used to, you're going to approximate that from secants, are the things that give you the instantaneous velocity. So that's kind of the big idea for this section, is thinking about, we have two things, secant lines and tangent lines, and we're going to use secants to approximate tangents. Similar with velocities, we can always calculate average velocities really easy. It's just a subtraction. So we can calculate those, and we're going to use average velocities to approximate instantaneous velocities. And we'll look at plenty of examples on Wednesday.